All right. Hi everyone, and thank you for joining our fourth and final test talk. My name is Sophie Legault. I'm Director of Product Management at EXFO, and I'll be your moderator for this session. Before we start, I just want to cover a couple of housekeeping points. First, for your best viewing quality, we do recommend that you use Google Chrome as a browser, and closing any other programs or browsers in the background. The chat window, as you probably see already, will be open during the session. We'll have a Q&A with our guests at the end. So we will be going through these questions, so please don't hesitate to put your questions in the chat directly. And also please note that after this live panel, we will have 4 in-depth technical sessions with our subject matter experts to get more insights. And I'll give you more details at the end how to get there. So in this specific test talk, we'll be discussing the challenges of 5G, going from R&D all the way through deployment. And to do this, I'm very happy to welcome our 3 special guests. First, we have Luis Miguel Contreras Murillo, technology expert at Global CTIO Unit at Telefónica. Welcome, Luis. We also have Harpinder Matharu, Senior Director, Technical Marketing Comms and Business at Xilinx. Welcome, Harpinder.
Thank you. Thank you.
And finally, Antonio Tartaglia, System Manager and Expert in Photonics at Ericsson. Welcome, Antonio.
Thank you, Sophie.
All right, so our guests will each go through about a 10-15 minute presentation, and at the end we'll have, as mentioned, our Q&A session with the audience. So now let's just dive right into it with our subject matter experts. Our first speaker, I'll hand it over to Luis.
Thanks so much, Sophie. So first of all, thank you. I would like to thank EXFO for the invitation to participate in this panel. Going to the topic, I think this very pertinent topic, this one of the 5G challenges when we take from the R&D to the deployment. And in this context, I will focus in one of the aspects. There are multiple aspects. So in my case, I will comment about the challenges that could be faced in the transport network. Challenges due to the radio functional split, which has been one of the major topics in the past. In fact, is yet being highly gaining momentum, let's say, with all the activities in Oran. Can we move to the next slide, please, Sophie? Yeah. So there is a clear movement in general in the industry favoring the disaggregation in several fields, in the transport network itself, but also in the radio part. And in the radio part, essentially, or the most representative movement in this direction is the way that is being, let's say, shown by Oran. The idea of having interoperability between the different parts of the functional stack in the radio. And there is clearly a movement in favor of that. Here I reflected in the slide a number of news regarding this. There is an initiative from the major European operators like Deutsche Telekom, Orange, Vodafone, and also Telecom Italia, which is not listed there, but is also part of this initiative. And I would like also to reflect here a couple of initiatives that internally from Telefónica we are fostering. We are doing some trials, some experiences in Germany and Argentina in this respect. This was recently appearing in the news. And also, well, these are tests in the fields, these are trials, but also we are engaged in having a better understanding of what could be the potential scenarios, the potential implications also in test environments as reflected in this participation in the second PlugFest from Oran. So essentially here the message is we are accompanying all this transition. We are going in that direction of taking what is coming from R&D, trying to understand what could be the impacts in the field. But it's okay, in this way, in this path, we need to understand the different dimensions, the different challenges that we could face. Next slide, please. So essentially, what could be the different implications? Where now, where we have before a kind of monolithic network, where essentially one base station and then some backhaul connectivity to the internals of the network. Now we are with this idea of radio functional split. We start facing some more diverse scenarios that bring new challenges. Essentially, we will have 3 different network segments: the front haul between the radio unit and the distributed unit, the mid haul between the distributed unit and the centralized unit, and then the backhaul as before. The associated challenges multiplies in these kind of scenarios, and well, I put there some of them. Probably there are some more, right? For instance, we have challenges associated to SLOs, to how to guarantee a number of indicators, a number of performance parameters in these services, that for each of the segments that we saw before, there will be different needs. And here we can talk about bandwidth, transport delay, jitter, flash rate, and so on so far. Also, we need to be conscious that, the starting point will be brownfield networks, and even if there could be new technologies that could solve or could be fitted specifically for some of these parts, at the end we will need to make all these technologies coexist and work together. And then we need to characterize what could be the behavior of different alternatives for each of these segments. And here we can find technologies or solutions like eCPRI, solutions based on conventional packet switching, optics, microwave, or even new technologies, new data plane capabilities like TSN or flexible Ethernet. Then a third challenge here reflected could be different protocols or different encapsulations being used for accomplishing the transport of, for moving the packets at the end from one point to another. And here also the variety in the transport networks is quite huge. We could find different encapsulations. For instance, in the CPRI, we could find native Ethernet encapsulation, or either encapsulation based on UDP/IP, or layer 2, layer 3 VPN solutions for implementing, let's say, the forwarding of the traffic, or segment routing solutions, IPv4, IPv6. So the multiple alternatives that we need to understand in order to assess impacts. Moving forward, also different aspects that we can find more, let's say, related to intrinsic properties of the network could be the topology. So we will have different scenarios, point-to-point, rings, stars. Also, the different decisions and solutions at the time of architecturing or dimensioning the network. So higher or lower concentration rates, the fact of we could have different distances for collecting the traffic for the radio units, for instance, number of kilometers that could impact on the delivery of the traffic. Also, the strategies that the operator could follow for concentrating or aggregating multiple sectors or multiple sectors or single sectors or so. And then finally, the different technologies in the radio part, in the proper radio part, that will imply at the end different impacts in terms of capacity and essentially in terms of capacity, like could be the 5G new radio, millimeter wave, and so. And finally, we need to be aware that the disaggregation will not be alone. Let's say we will need to make it to coexist with existing services, the 3G and 4G, because probably once we move in this direction, we as operators, we will leverage in the co-siting for taking profit of the footprint that we already have in the field. Also, essentially, in some cases, for operators that are not only mobile, we could be in aggregating other services, fixed services or enterprise services, and so. And finally, also, we need to reconcile all this diversity with the idea of slicing in the network. This is the next promise in the way of providing services. Next slide, Sophie, please. So all those challenges at the end imply to understand the different implications, the different combinations that we could face in the network, because there will be not just a single solution, right? Here in this slide, I presented just a number of, as a way of simplifying what could be this diversity. For instance, in terms of topologies, we could have a collocation between some parts of the radio functional split, like the ORU or ODU, the radio unit or the distributed unit, or being separated in different routers, and so on and so forth. This is just a small example, but the implications here are multiple. For instance, in the distance that we could find between the different routers, this will impact in the latency. This will impact in the potentially in the errors that could be experienced in the link, and so on and so forth. On the right of the slide, you see a number of parameters. I will not enter into detail, but this is just an example of for illustrating, let's say, how sensitive could be the different solutions, and then how the different combinations of alternatives could impact or could be appropriate or not according to the different scenarios to cover. So I will move to the conclusions for not taking much more time. So Sophie, thank you so much. So essentially, as conclusions, the radio functional split imposed very stringent requirements. We saw in the slide before in terms of microseconds for the latency, in terms of very low packet delay variation and very low packet error, and also limitations in the distance to cover, and so on and so forth. The transport networks are very diverse. There is a rich variety of technology options and also alternative engineering solutions for transporting the traffic, for forwarding the traffic from one point to another. So there is a lot of degrees of freedom in order to accomplish the solution. So it's essential to have a good understanding of what could happen, because at the end, going in one direction or the other could impact the overall service that would be the expected because the expected by the radio functional split. And for sure, these are all varieties in terms of technology, but also we need to add a new degree of freedom that could be also the variety in the implementation, so the different solutions from different vendors. So it's essentially to have a great overview of what could be all the different options, validate the solutions, assess the technologies, and assess also the vendors' implementations with the idea of, at the end, to extract guidelines and to ensure that once we move all of this stuff into the network deployment, the performance and we satisfy the performance, we satisfy the indicators that are demanded by ORAN, in this case, by the radio functional split. So as next step, essentially from the operator side, in this idea of 5G challenges, and in this specific context of the transport networks, at least our proposition from Telefónica is to be prepared to anticipate all these issues in the field. And for that, we are moving with the idea of establishing a stable testing environment for that, for getting knowledge of all of this, and so. And also being prepared for coming RFQs that could come in this area, in order to ensure that once we deploy the different solutions implementation, so we have some certainty that we will satisfy and we will accomplish the requirements that could come from the radio part from our radio colleagues at the end. So this was my presentation. I hope that could be of interest for all of you. Thank you.
Good. Thank you very much, Luis. This really highlights the different choices of technology that the operators have to make, and the challenges around them. So very interesting. All right, so our next speaker, let's go directly to Harpinder.
Okay, thanks, Sophie, and thanks, Luis. You set the stage with giving excellent perspective on 5G deployment challenges, and particularly emphasize on transport. So I'll build on the theme that you have started with, focusing on specific use case, and talk about transport challenges in 5G deployments and what strategies and perspectives, practices that we can leverage to overcome these challenges. Next slide, please. So as we all know, 5G NR is beam-centric technology. And from that perspective, global deployments of 5G today are predominantly using massive MIMO radios. And in this context, obviously, if you look at this diagram, you see that in a massive MIMO radio, we leverage a large antenna panel comprising of multiple antenna elements. By doing so, it enables the higher layer procedures to send multi-user data, which basically is combined with beamforming weights and coefficients to create multiple beams addressing multiple users at the same time, sharing the same spectral resources, thereby boosting the cell capacity. So essentially, massive MIMO systems, particularly sub 6 gigahertz, or what we now call sub 7.125 gigahertz, offer a significant promise of higher spectral utilization. And what we have seen is that the first wave of deployment starting from 2018 onwards, they were predominantly leveraging massive MIMO radios like 32TRX, starting with Korea, Japan, and then China, of course. In China, we saw a lot of 64TRX deployments. But overall, what we see is a significant number of massive MIMO deployments being used in 5G deployments. Next slide, please. Now, with massive MIMO deployments comes a significant challenge in managing the transport. So if you use a traditional split between radio and the base station, which is option 8, then we see that the throughput requirements or front-haul throughput requirements grows significantly. So taking an example of, say, 100 megahertz system with, say, 64 transmit and 64 receive antenna elements, what we see is that the overall system can deliver 5 to 10 gigabits of throughput. But on option 8, the interface between radio and the DU, the throughput grows to almost 160 gigabits per second to 200 gigabits per second. Now, this is quite a lot of front-haul bandwidth, and not many sites are equipped to really handle that, or in fact, very few sites can accommodate such an increase in front-haul transport. So from that perspective, industry has moved towards various functional splits that Louis mentioned during his presentation. So what we call as the 5G base station disaggregation is being governed by optimizing the system performance as well as the transport bandwidth. So now, for example, ORAN has introduced a 7.2x split, and very similar split is being used by tier 1 OEMs who have deployed these equipment already. And by doing so, what we see is that the front haul bandwidth has been reduced almost by 1/4. So in a 100 megahertz system, as an example, where we needed roughly 200 gigabits between radio and DU for option 8 split, for option 7.2 split, that drops down to 50 gigabits per second. And it's quite manageable to have two 25 gig links running between DU and radio. And this kind of brings down the cost of also the optics. So going to the next slide. Now this kind of expands into what ORAN, control plane, user plane, synchronization plane specification has introduced. So here you see that the ORAN spec in the two boxes at the bottom of this slide, you see that they have ORAN spec has introduced two concepts: category A radio, where the pre-coding happens in still the baseband, or what you call distributed unit, shown on the left-hand side. For this particular scenario, if you see, again, the same example case of 100 megahertz NR system, 64 antennas, 16 spatial streams downlink, and 8 uplink with 30 kilohertz subcarrier spacing, what we see is the downlink throughput requirement is for 7.2x split is about 50 gigabits per second, and uplink is 18 gigabits per second, as an example. And here, this is also leveraging compression. It's all the data is already compressed. Now, if we move the pre-coding into the radio, what we see is that now we can use much more efficient compression techniques like modulation compression on downlink in particular. And the throughput requirement drops down to 34 gigabits per second. And it's very important because there's a significant difference between more than 50 gigabits per second and less than 50 gigabits per second, because the number of optical modules or plugs needed on the radio side drops, as well as it kind of enables cell site to be scaled. But if we zoom into the downlink data throughput, if you see 34 gigabits per second, and what I've highlighted here is the data consumes only 12 gigabits per second in this particular configuration. Obviously, it can vary based on what configuration we look at. But surprisingly, you see that the control plane throughput requirement is more than the data plane throughput requirement. So obviously, this kind of highlights a problem statement here that in order to optimize the transport bandwidth, particularly the front haul connectivity to the cell site, which is always the constraint in the deployments, we have to look very closely in optimizing the control plane throughput while continuously enabling radios to become more intelligent to really deliver a higher performance. So next slide, please. So let's look into some of these strategies as to how we can optimize control plane throughput requirements. So O-RAN specification over time has introduced several features that enable reducing the control plane overhead. And even today, we see that some of the DU suppliers, they are still using techniques where they send beamforming weights. As you know, that beamforming weights are needed to combine the multi-user data in radio to generate the beams. And these beams then are talk to specific users using the same spectral resources. So even today, we see that DU vendors are sending beamforming weights on a slot-by-slot basis. And it basically adds to significant front-haul bandwidth requirements. Now, we are seeing a shift where the radios are being enhanced to maintain beamforming weight storage. So radios will maintain a dictionary of beamforming weights, and now DUs have to only send the index information as opposed to the entire beamforming weight for each slot, which basically is a significant overhead. So this is what we are seeing is this further reduces the control plane overhead. And then we are beginning to see that there are more features being added to the O-RAN spec that will aggregate the control plane packets. By aggregating control plane packets and having less headers consuming useful throughput across the front haul is a one very, very effective way. And then recently also O-RAN spec introduced concepts of sharing channel estimate information with the radio. And in this case, radio will do the beamforming weight computation and will maintain the beamforming weight dictionary. Although the transfer of channel information versus beamforming weights, it doesn't really help us in optimizing the front haul bandwidth, but there are multiple techniques that can be leveraged to kind of reduce the frequency at which this information has to be shared across DU and RU. So in summary, there are multiple ways we can optimize the control plane throughput, and this will continue to evolve as we are still in early phases of 5G deployments, and we are learning a lot of lessons from these systems that have been deployed. So going to the next slide, please. So this is a good example of how O-RAN spec is evolving, and primary focus of O-RAN spec is obviously to address a variety of use cases that are emerging in 5G, but also to bring up features or introduce features that help to alleviate transport throughput requirements. And we have seen consistently from the first drop of O-RAN spec in March 2019, from that time onwards, we are seeing major release happening every 6 months. So I think we will continue to see similar trends. As we learn more, I think more features will be introduced in standard specifications to create open RAN systems where we have true heterogeneous systems. That means any radio can talk to any distributed unit from any supplier, right? So which is what is the ideal goal of having plug and play base station deployment scenarios where you have much more rich ecosystem and supplier base that can provide individual components to help in 5G deployments. So going to the next slide, please. Now, as we know that though it helps to really continuously evolve the specifications to really help overcome transport challenges as well as introduce new use cases, but it creates a significant side effect in terms of ensuring interoperability. So as the O-RAN spec evolves, the specific version that is being supported by the deployed radio units and distributed units, it becomes quite a significant challenge to make sure that the heterogeneity is maintained in terms of the different suppliers providing radios, and DUs continue to use similar profiles, similar features so that they can interrupt seamlessly, as well as benefit from what features have been introduced by O-RAN or by even eCPRI for that matter to leverage and optimize the transport bandwidth. So this is a significant challenge. Obviously, EXFO plays a significant role here in terms of providing test and measurement equipment plus the test harnesses to make sure that DUs and RUs can independently do interoperability, and once they are put together or plugged together, they seamlessly work. So from Xilinx perspective, our DNA is to put together adaptable silicon technology for 5G radios and for acceleration and distributed unit. And by having this adaptability, it enables radios to accommodate new features as they emerge without having to bring down these radios or doing a big truck roll. So this is a significant benefit that we have anticipated, and we've tried to incorporate in our technology so that you can incorporate, operators or system vendors can incorporate new features as they emerge to optimize both the transport bandwidth as well as to implement new features, new algorithms as we learn more and more from the 5G deployments. So with this, I'll hand it back to you, Sophie.
All right, thank you very much, Harpinder. I think it's a nice highlight of the pressure on the bandwidth requirements for the frontal networks, and also all the OEMs and the standards bodies strategies to try and mitigate that. So it's quite a challenge there. So thank you very much. Let's go to our next speaker. So we'll go to Antonio. Go for it, Antonio.
Thank you, Sophie. Thanks a lot, and I'm really, really lucky to be the last speaker, as Luis Miguel and Harpinder have already addressed a lot of the challenges 5G brings in the radio and transport domains. And as an optical expert, I can focus on the challenges I see for optical solutions supporting 5G. Next, please. Next slide, please. Okay. I'll just say that with 5G, radio access network become ubiquitous and supporting a wide variety of use cases, a lot of which require increased capacity, low latency, and high quality of synchronization. Outside fiber plant assets also may become vital to be able to deploy 5G, and where they are scarce, the importance of their effective use is enormous. Next slide, please. One of the challenges of 5G deployment is that transport is no longer just transporting radio traffic. It must become an integral part of radio access network in order to support the requirements mentioned before: high capacity, low latency, high quality of synchronization, and effective use of transmission resources in all of the three domains: optical, IP, and microwave. But again, since I am an optical expert, let me focus on optical solutions. Next, please. One of the challenges I see for optical solutions supporting 5G, especially in the front-haul area, is often the partial understanding of what's needed to put optical solutions to work in the context of a radio access network. Most of the optical industry is focusing R&D efforts on optical solutions for hyperscale data centers, and for good reasons. What's difficult is shoehorning data center solutions into the radio access network space. While there are certainly some common requirements, large volumes, price sensitivity, a certain tendency towards short reaches, especially for distributed RAN, there are many significant differences too. I have summarized in a super simplified way on these slides. The different environment, tightly controlled indoor as opposed to outdoor cell towers exposed to the weather. Availability, 3 nines versus 5 nines with all the ramifications this brings on reliability. Fiber distance, especially for centralized RAN, distances can get longer and fiber can become scarce, while distributed RAN, as I said, is more similar in distances to data center interconnects. Capacity and granularity. We know data centers love fat optical pipes, 400G, 800G, 1.6 tera in the future. And it is to lower the cost per gigabit per second, and also because the spine leaf fabric interconnect can keep those fat pipes well saturated. In radio access network, we see the size of the pipes needs to be carefully dimensioned according to the capacity needed from the radio endpoints. And thanks, Harpinder, 25 gigabit today is important, and 50 gig and 100 gigabit being in the pipeline for tomorrow. Synchronization handling. Let's say it's hardly a concern at all in data center transport networks, but it's a vital importance in radio access network for some applications. And finally, last but not least, the cost of service. In an hyperscale data center, a technician with a bike or a Segway can cover literally a lot of ground and a lot of links, as opposed to cell sites scattered around the geographical area, which pose interesting logistics, cost, and even regulatory problems. Again, let me stress how important is high reliability of optical solution from this standpoint. Next, please. And the focus on data centers and hyperscalers is also reflected in the quite articulated ecosystem of standards and industrial fora defining optical solutions. Too few of them, in my opinion, are actually discussing the requirements of optics for radio. And I think there's for sure an opportunity to make the voice of optics for radio more clearly heard in this ecosystem. A challenge is represented by the fact that all these fora tend to cover specific angles of a solution, but there's none telling how to put together a solution from A to Z. Also, most of these bodies are consensus-based organizations. And if something is particularly controversial, some topic is particularly controversial, it's easier to remove it from the discussion table, and this might leave some holes in the relevant standards. Don't get me wrong, standards remain of fundamental importance, but in order to design a system, standards must be carefully collected in a meaningful way, and all the possible gaps must be filled. And the place where this normally happens is in a holistic system design specification. Next slide, please. Another challenge, which is not 5G specific, but exacerbated by the requirements of 5G radio access network, comes from the inherent complexity of the optical technology ecosystem and supply chain. What I'm reporting on this slide is a 3,000 miles view of the ecosystem building optical transceivers today. There are many players in the industry, many diversified business and supply models, and everyone needs to execute fast and under strong cost reduction pressure for the market. Let's say multiple sourcing is common at any level of the food chain: chips, packaged components, optical transceivers. And product redesigns to constantly align the cost base to market requirements are the normality. Now, when a complex ecosystem needs to move faster and faster under cost pressures, opportunities for mistake increase, but quality must not be compromised. Next slide, please. And this is the reason why we have system specifications and system integration tests at different levels, trying to intercept any possible or latent mistake as early as possible in the whole process. A latent defect becoming a field issue can have really serious cost implications. On the other hand, we know it will be pointless to test everything to death again and again. So the constant challenge here is to optimize test coverage at all stages with an eye to the cost, but the other one to uncompromised quality of optical solutions. Next slide, please. I'm going to conclude with an example of the importance of early testing. What I'm reporting here is the outcome of all optical transceiver samples approval testing we run at Ericsson when introducing new transceiver designs for whatever reasons: novel parts, redesigns, cost reductions. Well, a mere 5% of the samples is okay the first time we test it. About 50% has some easy-to-fix minor issues. 40% of cases has important issues requiring a major redesign and possibly several iterations with the vendor. And there's also 5% of the cases where there is some blocking issue related to a fundamental design flow requiring a total redesign of the transceiver. In most cases, its defect might have shown up as field issues of several degrees of severity if not intercepted. And I have to say, in many cases, the issue was generated by a partial understanding of the requirements of optics for radio. Again, I will close now summarizing in 3 words the challenges of 5G for optical solutions. And it's complexity, complexity, complexity at all levels. But that's why we have engineers. And that's why what engineers love to do, what we love to do, solving complex problems, don't we? Please, Sophie.
All right, thank you. Thank you very much, Antonio. Very, very interesting view on the differences in the requirements on optics for DCI applications versus RAN networks. That really pulls the transceiver manufacturers in very 2 different directions. So it is a challenge for the operators. So, and also the significant importance of testing those transceivers. So thank you for that. Yeah. All right. Well, thank you very much to our 3 speakers. Very insightful information. So we'll now go into our Q&A portion of the session. So I have received a few questions in the Q&A chat. If for the audience, please go ahead and add questions if you have some. So we have just about a 15-minute time frame for the questions. So I'll start with a question for you, Luis. Telefónica, with a few other European operators, have made a pretty strong commitment towards Open RAN. Can you expand on the timeline? When do you expect first commercial O-RAN deployments?
Well, I'm afraid I don't have the proper information to provide, because this is essentially being dealt by my colleagues from the radio group. So what we are working in the transport part is to be prepared for that. So and we need to be prepared in advance. So we cannot go to the deployment of the radio solution without having first assessed that the transport capabilities that we have will be good enough for supporting it. So somehow the clock is running for us. So independently that with this could happen. But let me say that also I commented at the beginning, we are now having some experiences in some countries like Germany and Argentina. So the deployment is not yet massive, but we are now going into that direction. So I would expect that in the time frame of 1 year or so to have a more generalized deployment on this. But I don't have the specific dates, and apologies for that. But anyway, we are working for now to have trying to have an assessment of what could be the solutions that we could implement in the transport for supporting that deployment in the radio, because we need to do so in advance.
Great. Thank you. Another question, maybe if someone wants to has the answer, it's not angled at anyone specifically, but the question is, what are the time-sensitive networking test points in the context of the O-RAN functional splits? Is there a need to validate TSN at the 7.2 functional split? Anyone wants to take that one?
So maybe I can comment as well, or please, Antonio Harpinder, please go, and I can go afterwards.
Yeah, please go ahead, Luis, so then I can chime in after that.
Okay, so TSN, as any other option, technological option, could have a place there. There are vendors that are offering TSN capabilities with the promise of improving the performance. And well, I mean, there is for sure an objective of testing those capabilities for understanding how it could be integrated in real solutions. So we, at least for Telefónica side, we are testing those capabilities. TSN is being considered also as a potential solution in the O-RAN specs in the transport part is being considered. Could be place of a broader solution. So yes, there is room for considering TSN or for testing TSN capabilities, yes.
Yeah, and
just go ahead, Harpinder.
Yeah, so just to add to what Luis mentioned, and probably this goes back to Luis, what you had shared in your presentation, that we need to support multiple protocols and these deployments, and definitely TSN is one of them. And obviously, O-RAN spec has gone and defined synchronization requirements very in a detailed manner, and basically cover broad set of use cases. And as we know that as we are moving to eCPRI, so primarily everything is gravitating around 1588, and then the synchronization plane has been defined to address a variety of use cases. So obviously, based on what protocols are available and what protocols are in use at a particular cell site or a deployment scenario, these protocols will come into use as well.
Yeah, let's say as an optical expert working at layer 0, the best I can do is to make sure that any optical solutions we define does not tamper with the quality of synchronization in any way. For instance, not adding unnecessary sources of timestamping error or of a timing error budget to 1588. So the optical transceivers for radio, again, need to be robust also from that perspective. They must not tamper with quality of synchronization.
Great, thank you. All right, our next question goes to Harpinder. So in the context of Open RAN industry initiatives, we often come across proposals for keeping radio units as simple as possible. Is it feasible and the correct approach?
Right. So this is a good topic that is getting a lot of attention, and a lot of times it's a desire to keep radios as simple as possible, so that it enables easier upgrades, configuration, as well as reduces the truck rolls to the variety of sites, and bringing in more complexity into distributed unit, which is where new technologies around virtualization as well as using heterogeneity is being deployed to help overcome some of the complexities. But the key point here goes back to that you have to look at the problem at hand, which is the transport bandwidth requirements, particularly the front haul bandwidth requirements, which will necessitate us to shift some of the functionality into radios to manage that, because this is quite expensive proposition to really make radios very simple, but push a significant amount of data to these radios, because essentially with massive MIMO, with 5G, wide bandwidth spectrum that is available for 5G deployments, it's simply not possible for us to keep radio as simple as possible, as desired within the industry. So it has to be a good balance between optimizing the transport bandwidth as well as keeping the complexity of the radios to a reasonable level, so that it's a good mix of intelligence in radio plus functionality in distributed unit.
Great, thank you. All right, our next question to Antonio.
Yep.
Antonio, there's a general trend towards commoditization of hardware, where networking gear becomes low-cost appliances and optical transceivers become low-cost consumable. Is the money spent on testing really worth the effort, especially for low bitrate, short reach optical transceivers?
Yeah, this is a question coming back periodically. And my short answer is yes, it's well spent money. I understand the concern. Now, for certain simple type of optical transceiver, the cost is in the ballpark of a few tens of dollars. Is it really worth spending so much time and effort in testing a $10 or $15 or $20 optical transceiver? And the answer is it depends. If it's an IT consumable, if it's the transceiver in the NIC of your server, maybe not. I don't know. It's not up to me because I don't know. Up to me to say because I don't know the operating model behind. But I can tell you, if you send millions of low-cost transceiver out in the field and something goes wrong, even if the transceiver is inexpensive, the cost of lack of quality is orders of magnitude, many orders of magnitude more expensive. So it's well worth it, I think.
Great, thank you very much. Our next question is for Luis. Luis, Telefónica was a host for ORAN TIP Transport Plugfest last fall. Can you share on some of the key lessons learned and recommendations going forward? All right, I will maybe go. I think Luis is frozen. I don't know if it's if it's the same for everyone. So maybe we'll move to the next question and see if Luis comes back to answer the question. Maybe a question for the other two members. Not sure which one. Is the Okay, we'll continue. So is the HARQ loop latency a significant problem? I'm not that familiar with that term. So the minimum spec is 100 microseconds, but what are the actual budgets seen in deployed kit using eCPRI in the field? Anyone wants to venture on that one?
Yeah. So again, I'm not an expert in terms of, or I don't have visibility as a silicon supplier as to what is being seen for hybrid ARQ latencies in the field. But eCPRI standardization as well as ORAN defines a certain maximum length that will meet the budget of a typical base station. So it's 30 kilometers and such, right? So the synchronization parameters are very well defined in eCPRI, which basically dictate as to what kind of budget each block in a base station on distributed unit side and on the radio side has in terms of performing, whether it's the physical layer function or on the radio side doing the beamforming or digital front end. So these are very well defined within the spec, and typically for any deployment we'll keep sufficient margin, right, so that it's we don't exceed any of these budgets. And then on top of that, hybrid ARQ in sense has been defined with sufficient margin to really accommodate any repeat transmissions that we need to send. So I think this has been something that has been carried over from 4G. So 5G doesn't really introduce something dramatically new in this particular area. So I think we are leveraging what experience we have gathered from 4G deployments in the past for this.
Mm-hmm.
Perfect. Thank you. Luis, I think you are back, right? Okay, I can see you. I don't know. Great. Did you hear the question that I asked, or I'll repeat the question? Just okay. So I'll repeat the question. Okay, perfect. So question to you was, Telefónica was a host for the ORAN TIP Transport Plugfest last fall. Can you share some of the key lessons learned and recommendations moving forward?
Let me provide some quick answers, so not very much thinking on the answer before. So essentially, the complexity of the complexity and variety of solutions. So there is not a common pattern, and this makes clear makes evident the need of testing and having a clear definition of test in order to be able to compare and to benchmark the different kind of solutions. So it's not a matter of simply implementations per vendor, but also technology options. So there is a rich variety of options. So very difficult, let's say, to reach a common pattern. So for that, the need of having in advance well-defined test scenarios and environments. And so it's essentially, I would say that the main message is essentially that this reinforces the need of having testing, of spending time and effort on testing, because otherwise, when we could have we could not get a clear view of what we can deploy in the field. So very worthy to test in advance and to explore the different alternatives. So there is not a single pattern. There are different options, and we need to work hard on that. And also not only because of the options that could be available, let's say, but also because, as I mentioned during my speech, we depart from a greenfield scenario. So we need to assess even how the new technologies could be integrated with the existing ones. Because at the end, from the service perspective, we need to offer the same performance, the same experience, or the same SLA guarantees, either with different technologies. So probably that would be the key message. No, that is an effort that we need to continue keep working on that. Yeah.
Mm-hmm. Challenging indeed. Yep. Thank you. All right. So we have time for one last question for Harpinder. Harpinder, how can we overcome interoperability challenges between DU and RU in Open RAN deployments?
Yeah, that's a very interesting topic again. So first of all, it's important to understand that we can, as Luis mentioned, there is a goal for having heterogeneity in the sense, we want fully plug and play where different RU vendors can talk to any of the DU vendors to have a heterogeneous Open RAN deployment. So as we see today, it's homogeneous where a single vendor is providing both RU and DU. So in this context, when we are marching towards heterogeneity, interoperability is a very critical step. And at the same time, as we know that most of the standard specs, they continue to evolve. So it becomes quite challenging to really keep the interoperability between the RU and DU vendors. And that's where I think defining profiles as these have been defined in ORAN now, because ORAN spec is quite flexible and broad in scope. But now we have profiles that have been defined. And then also working very closely with test and measurement vendors like EXFO to make sure we have a right set of setups to test for a variety of ORAN profiles. So I think it's going to be a complete supply chain working towards ensuring that we have the right setups to have a compliance check and then doing a plug and play in the field, just like the way it happened for PCI Express, for example. PCI Express plug face, where we could go and test independent boards, and then those boards will plug seamlessly in any server. So similar setup needs to happen where multiple suppliers, multiple vendors will have to play a role. And that's what needs to happen. And obviously, operators have to enable these plug face, as Luis mentioned, some of the plug face happening under the auspices of TIP to achieve the similar goals. Yeah.
Yeah, thank you. Yeah, I'm sure we're bound to see many of these plug fests in the next few years, as we did for other technologies. It's a key element to drive interoperability. Thank you, Harpinder. All right, well, that comes to the end of our Q&A session. Thank you very much to our speakers. As mentioned, very insightful information. So very good to hear you. Now we will move to, in a few minutes, for our audience, you'll have the opportunity to go into our more in-depth sessions for 5G field and lab deployments. So the way to get to these sessions, there's actually 4 different sessions running in parallel. Each of these sessions will be repeated twice, so 30 minutes each, and each is repeating twice. So you have the opportunity to attend 2 of the sessions. It's very simple. You go back to the lobby, into the environment that you're in, and then you select the session that you want to attend and just log in and meet our experts for these different sessions. So thank you very much again to our speakers. Thank you to our audience, and for the questions that have not been answered, we will answer them through email. Thank you very much. Have a good day.
Thank you.
Bye-bye.
Bye.
Thank you.
Bye.
Bye.